Last class we discussed about Euclid's algorithm for finding GCD of two integers. Today we are going to discuss an extended Euclid's algorithm which is useful in finding modular multiplicative inverses. The application that I just mentioned we shall discuss later, and the agenda for this lecture is to discuss about extended Euclid's algorithm. Let us recall the basics from number theory that we use for proving the GCD recursion theorem, which is the theoretic background for the Euclid's algorithm. In lemma 1, we proved that if D is a common divisor for A and B, then D divides any linear combination of A and B. Linear combination means A multiplied by an integer plus B multiplied by an integer. And in theorem 2, we proved that for any integers A and B with one of them non-zero, the GCD of A and B is the smallest positive linear combination of A and B. And as a corollary, we have when D is a common divisor for A and B, D divides the GCD of A and B. Because GCD is a linear combination and the common divisor divides any linear combination. And this is the GCD recursion theorem that we proved in lecture 24, which proved that for any non-negative integer A and a positive integer B, GCD of A and B is GCD of B and A mod B. And these are the results that we used in the Euclid's algorithm. This is the Euclid's algorithm that we discussed in the previous lecture. And from theorem 2, we know that GCD of A and B is the smallest positive element of this set, that is the smallest positive linear combination of A and B. That is theorem 2. So, for any integers A and B, there exists two other integers x and y such that GCD of A and B is ax plus by. This is what theorem 2 tells us. And finding the values of this x and y satisfying this equation is useful in computing modular multiplicative inverses. This is an application. With that motivation, Euclid's algorithm can be extended to find the values of x and y such that the GCD of A and B is ax plus by. Now, how to extend the Euclid's algorithm for finding the values of x and y? Suppose we extend it to return a triple dxy. The original Euclid's algorithm is returning only d, which is the GCD of A and B. Here we need to extend it to return also x and y such that d, which is GCD of x and y, is equal to ax plus by. So, we want to find x and y such that the GCD is a multiplied by x, the first argument multiplied by x plus the second argument multiplied by y. Now, when b is equal to 0, GCD of a comma b becomes GCD of a comma 0. By definition, it is a. Here, when b equal to 0, we can have GCD of a comma 0 is a. By definition of GCD of a comma 0 is equal to a, and a can be written as A multiplied by 1 plus B multiplied by 0, this becomes 0, so this is A itself. Now you see we are getting GCD of two values as A, which is written as A multiplied by 1 plus B multiplied by 0, it is in this form. So if you carefully look at what we want is from the extended Euclid's algorithm, we want to return the GCD, the value of x and y such that the GCD is the first argument multiplied by x plus the second argument multiplied by y. So this is in that form. The GCD is obtained as A, which is the first argument multiplied by 1 plus the second argument, which is 0 actually in this case, multiplied by 0. This is a solution, any value for y will do, but this is also a possible solution. So of course you can return dxy as a10, dxy as a10. So we have solved the base case where when b equal to 0, what we can return from the extended Euclid's algorithm is a10 as this triplet. Now we need to see what we can do for the case when b is non-zero. When b is non-zero, we know that the Euclid's algorithm by using the GCD recursion theorem will make a call GCD of b and a mod b, because from the GCD recursion theorem we know that GCD of AB is same as GCD of b and a mod b. So naturally what the extended Euclid's algorithm will do, it will return a triplet for this function call. Suppose it returns a triple d prime x prime y prime. The extended algorithm is to return a triplet such that d prime is the GCD of these two values, and which can be written as the first argument into x prime plus the second argument into y prime. Thus we have GCD of b comma a mod b is equal to d prime if it is the triplet returned, and which can be written as, this is what this equation is telling, the first argument b into x prime plus the second argument a mod b into y prime. This is what we know. Now observe that this is exactly what this equation is telling us. The GCD of two values a and b is d, means it can be written as the first argument into x plus the second argument into y if the returned triplet is dxy. But here the returned triplet is d prime x prime y prime. So the GCD d prime can be written as the first argument into x prime plus the second argument, that is this, into y prime. So no question, this is what we need. Now this is what the function called GCD b and a mod b returns. Now we want to see, utilizing that, what is the original triplet dxy that the extended Euclid's algorithm can return when b is non-zero. We can rearrange this equation and find it. So here what I did is, I have substituted a value for a mod b using the division theorem. Recall that from the division theorem, for any integers a and b, you can have this equation. Any integers a and b satisfies this equation. A is equal to b multiplied by the quotient of dividing a by b plus r, which is the remainder of dividing a by b. This is division theorem. I hope you remember it. Otherwise, please go back to that lecture and see that this is exactly the division theorem. In this case, q is nothing but the quotient of dividing a by b and r is the remainder of dividing a by b. Now if you look at what is r from this equation, you can see that r is nothing but a minus qb. Now you substitute the values of q and r, you will get it as a mod b is equal to q, which is this, multiplied by b. And this is this value of a mod b I have substituted in this equation. Just verify it. I have replaced a mod b with the RHS of this equation. Okay. So this is what we have. Now in the second term of this plus, you take y prime inside, multiply y prime inside, you will get a multiplied by y prime minus this quantity multiplied by y prime. Now you see that it is like b multiplied by an integer plus an equation, a multiplied by an integer plus b multiplied by another integer. So we want to get an equation where it is of the form a multiplied by an integer plus b multiplied by an integer. That is what we need. We need d prime as a linear combination of a and b. We can write it. We can take this term first, that is a y prime, plus from the other two terms I am taking b as a common factor. So b multiplied by, from this term I am getting x prime, plus from this term if I take b out, what is the remaining? This is quotient of dividing a by b multiplied by y prime. So we have not done any magic here. I have taken this term as the first term, plus from the other two terms I am taking b as a common factor. So x prime minus these two except b. Okay, so this is what we are getting. Now you verify that this is the linear combination of a and b, a multiplied by an integer plus b multiplied by an integer. So this is of the form a multiplied by an integer plus b multiplied by an integer, where we are multiplying y prime with a. So this x is nothing but y prime, and what is multiplied as y here? This quantity. Thus we have dxy, which is what we need to return from the Euclid's algorithm. In terms of this triplet, we can have dxy as d prime, y prime, and this quantity. Why? Because from the GCD recursion theorem we know that GCD of AB is same as GCD of B and A mod B. So this call is returning GCD of B and A mod B as d prime, which is same as GCD of B and A mod B. Sorry, GCD of A and B, and that is why we take d as d prime, because from the GCD recursion theorem, GCD of AB is same as GCD of B and A mod B, which is returned as d prime. So that is okay. Now you verify that what is the quantity multiplied with y A, which is y prime, and that is why you are taking the quantity integer that you have to multiply with a as y prime, because it is y prime here. And what is the integer quantity that you have to multiply with b? That is what you need as y, which is nothing but this quantity, and that is exactly what we are doing here. I hope you are following. Otherwise, watch it again and verify that what we have done is correct. Proceeding. Now we have these two conditions. We need to know what is the triplet dxy that we can return from the extended Euclid's algorithm. We found that when b is 0, what is to be returned is a10 for the call GCD of a0. When b is non-zero, what is to be returned is this quantity. You make a call to GCD extended Euclid's algorithm, and assuming that it returns this triplet, then this is what you have to return from the algorithm. So when b equal to 0, we found that we have to return a10, and that is what you are doing, returning a10. And when b is non-zero, you have to return what? D prime, y prime, and this quantity, exactly what we found here. D prime, y prime, x prime minus the quotient of dividing a by b multiplied by y prime. No need to by heart, you just verify that this is exactly what we found. So you set dxy as this triplet and return dxy. So this is the extended Euclid's algorithm. Now you see that you are not only getting the GCD of a and b as d, you are also getting x and y such that d is nothing but a multiplied by x plus b multiplied by y. Maybe we can look at an example execution for the extended Euclid's algorithm. You take the arguments A and B as 99 and 78. B is non-zero, so the else part will go. You will call Euclid's algorithm with B and A mod B. This is the value that you can verify. Again B is non-zero, so you will make another call with 21 and 78 mod 21. Again non-zero, so you will again make a call with the 15 and 21 mod 15 is 6. Again you are making recursive call with the 6 and 15 mod 6. Again you are making with 3 and 6 mod 3 is 0. You are getting into the escape situation where B is 0. So what you have to do? You have to return A, which is 310. So you will be returning 310 as the triplet dxy. Now naturally you are getting back return value to this d prime x prime y prime, right? So this value of dxy will be returned as d prime x prime y prime. Then by using this equation you find the value of dxy for the previous recursive call. So you can verify that these are these values. Why? Because this is what you wanted to do. X is same as y prime, right? So what is x? D is same as d prime, that is what we know. D and d prime are same. So d and d prime have same values. And what is x? X is nothing but y prime. So x is getting the value of y prime. And what is y? Y is this equation. Y is this equation. You substitute the value of x prime, which is 1, minus this is 2. We have obtained the quotient of dividing a by b as 2 here. So 2 multiplied by y prime is 0. So if you solve the equation, you are getting it as 1, and that is why y is obtained as 1. So this is what we did. Now this triplet will be returned as d prime x prime y prime for this instance. So you will get this. Verify that it is correct. D and d prime are same, and x is nothing but y prime. 1 you are obtaining here. Now you applied the formula of y. It is this equation, and x prime is 0, and this quantity is obtained as 2 here. And what is y prime? Y prime is 1. So equation is this. If you solve it, you will get it as minus 2, and that is why you have minus 2 as y. Now what is going to happen? This triplet is going to become d prime x prime y prime for this recursive call. And so you obtained dx and y. Verify that it is correct. D is same as d prime over here 3, and what is x is nothing but y prime, so it is minus 2. And if you apply the values in this equation, x prime is 1, this quantity is 1 obtained as 1 into y prime is minus 2. If you solve, you will get it as 3, and that is why you obtained y as 3. Now what will happen? This triplet will become d prime x prime y prime for this function call. So you obtained the values of dxy in terms of these. Verify that it is correct. D and d prime are same. X is nothing but y prime, so you are getting x as y prime, and now you are getting y using this formula. X prime is minus 2. A divided by b, the modulus of a divided by b, the quotient of dividing a by b is obtained as 3. So 3 multiplied by y prime is 3. If you solve it, it is nothing but minus 2 minus 9, which is minus 11, which is what you are obtaining as y. Now this triplet is going to become d prime x prime y prime for the first recursive call, and you obtain the dxy in terms of these by applying these formulas. Verify that it is correct. D and d prime are same, and what is x? X is nothing but y prime, yes, minus 11, and now substituting the values of x prime, which is 3, quotient of dividing a y b as 1 multiplied by y prime minus 11. If you solve it, 3 minus 1 into minus 11 is 3 plus 11, which is 14, and that is why you obtained y as 14. So the algorithm returns the triplet as 3 minus 11, 14, and you can verify that the GCD 3 can be written as the first argument multiplied by the value of x, which is minus 11, plus the second argument multiplied by the value of y, which is obtained as 14. And from the theorem 2 we know that 78 and minus 11 and 78 are the values of x and y, which will give you the smallest positive value for ax plus by. So the extended Euclid's algorithm is now applied to find values of x and y, such that you are getting the GCD as ax plus by, and later we can see that the values of x and y that we obtain like this is useful in finding the modular multiplicative inverse, which we need in various number theoretic algorithm. With this we are finishing this lecture. Today we looked at an extension of Euclid's algorithm, which extends the basic Euclid's algorithm finding the GCD of two numbers a and b to return, in addition to the GCD, the values for the integers x and y, such that the GCD of a and b is a multiplied by x plus b multiplied by y. Thank you.